Good evening and a warm welcome to the SES webinar on dome structures. May I now introduce you to the moderator and speakers for today. Let me first introduce you to the moderator, Dr. Abhay Gupta, Director, Skeleton Consultants Private Limited. Dr. Abhay Gupta has more than 35 years of experience in the field of civil engineering construction and structural designing, and also teaching research with several academic research and development institutions and BIS. He is dynamic, multi-dimensional civil and structural engineer with vast experience in the areas of RCC and steel designing, construction management, teaching and research, and team building, imparting leadership to a group of people in pursuit of achieving individual and organizational goals. Currently Director of Skeleton Consultants, Dr. Gupta has experience of design, coordination, review, mentoring, execution, etc. for more than 500 projects of RCC, steel building, industry, and infrastructure sector. Now our speakers, Bal Kulkarni, Chairman Delcons Consultants India Private Limited, a BE Civil and MTech Structures with over 30 years of experience. Bal Kulkarni is the Chairman of Delcons Consultants. He is a member of Institution of Engineers, Fellow of Institution Valuers, American Concrete Institute member, and Indian Society of Structural Engineers member. He is also an author to many technical papers. Up next, Shirish Ramesh Kembavi, Partners Environs. With Masters in Architecture, Shirish has handled projects across various residential, institutional, master planning, and heritage sectors. He is a visiting faculty at Ayojan School of Architecture and Design, Pune, with PVP College of Architecture. He is also a member of Associate of Indian Institute of Architects and is also a fellow member and secretary Institute of Urban Designers India, Pune Center. Up next, Nilanjan Basu, founder Basu Consulting Engineers. An ME in Structures is a structural engineer having more than 20 years of experience in his field. He has worked in diverse projects involving design and detailing of RCC, steel, and composite structures. His proficiency domain ranges from steel plants to cement plants, oil refineries, airports, multiplexes, etc. He has authored engineering design publications for 40-storied building, shopping mall, some multiplexes, etc., along with textbooks on basic C++ and Java. He hopes to encourage future engineers to take up the challenge of building a better India through their knowledge. Requesting all the attendees to please participate in the poll and do write the name of the speaker whom you would like to address during the Q&A session. Also do subscribe to our YouTube channel, SCS TV, for steel construction updates. Before we start the discussion, I would like to hand over to Carol for a quick announcement.
Good evening, everyone, and a warm welcome to the webinar. Before I hand it over to our able speakers for the further session, I would quickly like to make a small announcement. We are having a very interesting workshop coming on the 18th of September on building codes. For the purpose of the same, we are running a poll, so do participate in the poll and let us know your feedback. And the registration link for the same is in the chat box. Do register for the upcoming webinar. Thank you. Over to you, sir.
Over to you, Mr. Kembavi.
Good evening. The project that we are going to present today is the legislative wing of the Pune Municipal Corporation in Pune. Now, Pune is the second largest city in the state of Maharashtra, and the municipal corporation of Pune came into being in the year 1950. And today, the overall area of the city is about 350 square kilometers, and it has a population of about
1 second. Can everyone see the screen?
Is the screen visible?
No, sir.
Sorry?
No, sir, it's not visible. If you could screen share.
Just a minute, there seems to be some glitch. Yeah, is the screen visible now?
Yes, sir.
Okay. So sorry for that. So the as I said, we are going to present the Pune Municipal Corporation extension building. So the Pune Municipal Corporation, which was established in 1950, had their first building built in the year 1957, and now thereafter, in the year 2018, the new extension was planned and constructed. And if we see the site, the old building shows is in the form of a small letter H, and then there was a large courtyard in which this legislative wing was supposed to be added. Now this legislative wing was to house all the public facilities, the offices of the municipal secretary, the mayor, all the office bearers, the general body, and the public visiting gallery. And it had two large basements. So basically, uh, this was the kind of an insert that was planned. Now, if we look at the section of the new building, it has two levels of parking, followed by the public spaces, then various offices, and then the general body hall. So the main challenge, the basic challenge was to arrive at a structural grid which would do justice to this variety of spaces and the needs of the halls and the conference halls and all that was there. So to arrive at a mean kind of a grid which would suffice all this, and then that grid would lead to a base of the general body hall and the dome subsequently. So that was the first challenge. So you can see the various layers of the floors. So there are two levels of basement, and then there are four levels above. The topmost level is the general body hall and the visitors gallery, from where they view the proceedings of the general body. Now this is the first level where it's the public spaces. Then you have the office bearers rooms. Then we have the mayor's chambers and the proper general body hall. And then you have the visitors gallery on top. This is the plan of the basement. So we have arrived at a grid which is sort of taking care of all the spaces there. Now this is what the earlier building kind of looked at. This is a rendering of that. And the empty space that you see between the two buildings was the space where this new building was proposed. And this is the view with the new building inserted. So you can see that we have carried over the same architectural vocabulary in terms of the finishes, in terms of the fenestrations, in terms of the architectural elements, so that it appears to be a seamless extension of the old building, which has a strong architectural language of its own. So this is what the empty space was, and this is how it looks after the insert. And the dome that you see on top, which has got a stone-like finish, is the dome that covers the general body hall. Since the general body is the place where the people's representatives, kind of sit and discuss the affairs of the city, it has been given the prime importance because that is the most important place in the whole building, and that has been celebrated with a dome. Now coming to the level of the dome, since if we see the earlier thing, the dome is quite set inside the building. So it was not possible for us to do any kind of a prefabricated thing and install it on the building. So this building, the dome starts at about 20.5 meters from the ground. So it was done in segments. This is the various ways in which the whole thing was erected. So you have the central compression ring, and then the various petals that were connected to it. You can see the various ways in which the units were fabricated and then sort of assembled on the site. And then as all the structure was erected, it was connected with horizontal purlins. And then the whole structure was cladded with GRC panels, that is glass reinforced concrete panels. And then from inside, these acoustic panels were hung for the acoustical purpose. On the bottom right, you can see the final view of the building with the dome. So this is the work in progress photographs. You can see the glass reinforced concrete panels which are being connected to the purlins. Inside the glass reinforced panel, there are plain pre-coated sheets as a layer, and then after the entire thing is finished, it is painted. Now the dome has got triangular windows, 16 of them, which let in natural light. So this was also a design feature, but also a challenge for the designer, the structural designer, to make it happen at the base of the dome. But it was successfully met. So this is how the whole ensemble looks, with the old and the new structure gelling with each other in terms of finishes and the architectural vocabulary. These are the interiors of the space. This is the general body hall, and you can see the visitors gallery on the upper floor, the mayor's desk and all the office bearers. Another view looking at the mayor's seat and the press gallery at the back. And this is the ceiling with the triangular windows letting in the natural light, the suspended acoustic panels, and the structural ribs which are there are not hidden, but they are celebrated in a way because they speak how the structure functions and how it has been conceived. So this is the building. Now I hand over to Mr. Bal Kulkarni, the structural consultant of the project, for the structural analysis and the logic of the design. Thank you.
Thank you, Shirish. And first of all, thank you, Manisha, for your very kind introduction. And we will go on to basically the presentation for the structural part. We have tried to keep the presentation not into the very intricate details of the design. But while doing this, as Shirish said, we faced lots of problems regarding the erection, and we had to think of all those things during the planning of the building itself. As Shirish said, we had to select a grid which would later on give us that much of open space. So we selected around 7 meters spacing for the columns below, and then deleting 2 columns. So we would have a 22-meter grid on top. And also, why? I mean, as we see, normally we say that domes are the kings of roof, which has been the heading here. It is mostly called that because people think, I mean, I would tend to disagree with that a dome is very easy to construct. It is monolithic, it has a single material, no angles, no curves, etc., etc. In Indian mythology, we normally prefer domes for covering our most coveted places because it is a sign of perfection, eternity, heavens, etc., etc. So you see all the major buildings in the world, they would have a very prominent dome covering their most important places. So we come back to the building. As you see, this is just a structural frame model of what we planned. The building was two basement levels for parking, then 4 upper levels. These 4 upper levels also had intermittent mezzanines, and that is why you see all these 7 different levels. And as we go up, I have just put in this slide for you to understand how we what is the position of the dome on top, and it is, as he said, at the rear side of the building. And because then the entry to that also had to be interconnected to the existing building which is there, so people would walk in from that building also. We have designed an interconnecting bridge there, and also many others would come from the front side, so both the roads could be accessed, and this dome would happen. So it is again seated on a 22-meter by 22-meter square grid, and that was the, you can say, first challenge for us to generate a circular base on this square, so to say, because our lower structure, our structural framing was squarish or rectangular, so to say. So now we had to start to, sort of build a circle inside the dome. So I'm just sharing you some photographs. This is just a detailed section, and for you to understand, this, as he said, was 20-meter above the ground level. This building is covered from three sides, is, so to say, hidden from three sides because of the old building. And the front side is a very flowing road. It is a main bus stand of, you can say, the Pune Corporation, where the bus density, bus traffic is huge. So for us to fabricate something on that ground, and maybe, call up cranes and pull it up, and fabricate it elsewhere or fabricate it on the ground and put it up, was also a big challenge. You can see here, I have in this section, elected representatives general body hall. That was the place we chose where we could do our fabrication here, and then try and put up it on top here. So generally you can see from our working space, we are nearly 20 meters up to the top. The height of the dome is 11 meters, and then we had to make lots of provisions from the beginning itself. It was not possible to fabricate all the petals, etc. there, but we did most of the work elsewhere, and we had to bring it. The purpose of doing this, not as a monolithic structure, were twofold. One, that we could fabricate it in pieces, and next, as the architect wanted these windows below. Normally, as we know, all the load is transferred at the base, but then having those huge openings at the base, we had to make a sort of a skeletal structure to ensure that we could have these open spaces in between. These are just some of the images that we used for our structural members here. So I would just go on to the actual structural framing. If you see here, this shape, as you say, in a sort of a star, we use this concept of having these 157.5 degrees angles to generate a 16 noded polygon on top of the square that we had put up. Because that 16 noded, you will also realize in our IS codes, for our loading purposes, a 16 noded polygon or something more can be treated as a circle, and then you could use all those parameters for circular structures, or shape factors, etc., etc. So we have used this 16 noded element here, and you can see that this is the front, this is the plan view with the square and the circle inscribed in the square, and some outages beyond the square. We'll just come to the requirement of those spaces outside also. The normally nowadays we look at photographs from the ground level or a little higher, but nowadays with the drones we also have to look at the plan, and we have to ensure that plan also look good. So this star shaped configuration also, we ensured that it looks good from top also. Now we'll just go to how we formulated the whole dome. As we see, we have 4 main trusses here spanning 22 meters on the RCC columns below. Here is just an image of the total structure of how every element was eliminated, how was erected, so to say. And then we started first with these 22-meter trusses. These trusses, you can say, these were the main load carrying members. From there, we had to ensure that these intermediate trusses will not hamper the view of the inside of the dome. So the inside of the dome, so that a circle is inscribed in this, and whatever are the tangential areas become these, so to say, intermediate trusses. So we had the main trusses, the intermediate trusses, which forms not exactly the base, but you can say near around the 16 noded elements here. So this is how it looks when we superimpose these intermediate trusses on the main truss. So we get something here. And then normally when I'm looking at the design aspects here, I have one truss which is 22 meters. For the lateral restraint, I can have only these trusses, but that leaves nearly 11 meters in between, which is unsupported, which would have made the whole structure very heavy. So we have added these added members. Now this we had to take care in the design. So rest of the whole structure is an RCC slab, but these portions we have retained as structural steel. We have done them in structural steel with a deck sheet slab so that we are able to superimpose these trusses on them. And then this truss also gives me a lateral stability for my truss. So you can say, I can say my whole truss, I have ensured that it is at least laterally supported at every 2.5 meters. That gives me lots of leeway in my design. Then once we have done this, once my base is ready, then we go on to erecting the petals. As I told you before, we had these windows here. So we ensured that those windows would come in between. We are calling this petals. We would normally prefer to call them as ribs. So we, instead of having that monolithic structure, we planned on having a skeletal structure. Because these ribs could be individually fabricated some way, we could bring them here and we could, try and erect it one by one, because that would reduce the weight required for the erection. As I told you, we were at a much higher level. I've just shown you the sub trusses here, which are on the inside of the square. On these, we are now starting with the erection for the petals. These petals are again interconnected by the purlins, or there we can call them purlins or support for the glass reinforced panels that we are doing. This helps in screwing the glass reinforced panels to the dome. Those glass reinforced panels was also a big challenge because we had to make a sort of a template at every level to ensure that all the curves and slopes were exactly correct. This, you can say, is now the completed feature of the whole dome with my main trusses, the intermediate trusses, and the skeletals or the ribs going up and connecting to the compression ring, and the intermediate purlins. What I have not shown is some diagonal bracings that we use. These are not shown in this drawing, but you will see them in the later drawings. As I told you, these other supporting trusses were also important because they offered me the lateral restraint for these main trusses. So you can say this is generally the whole configuration at the bottom, which we had to generate. The truss at the bottom, the 22-meter truss is about 1.5 meter deep, and it is prepared by two channels. I will just take you along of why we had to choose this particular geometry or these particular sections, because see, this is a cross section of the building, and as I told you, this yellow location you see is the location that we were able to use for bringing the fabricated elements here, and then we had to erect everything from here. So my truss is here, it is on top of this roof, it is here. So my truss had to be erected from here. We had to ensure that my laps, etc., are at appropriate positions. And once these trusses were erected, my petals would be erected from here. So this around 8-meter height had to be negotiated first. Then we come to the roof, because the roof was not so big to be able to place all this. And again, picking up so much, this whole structure would weigh around 350 tons. So bring everything up here from the sides, keep these on the slabs, and then try to erect them would have been very difficult. And also, during the design stage itself, what we planned was we are going to use this space here for our erection methods. And for that, when we began the erection, First, what we did was we propped all these slabs from the ground level upwards up to here, because we needed to erect some derricks here for using them as erections. When we had planned these skeletal structures, we were also trying to see whether we could use the main structure of the dome itself to erect the secondary structures. But after some detailed analysis, we realized that that would take too much of, that would add, that was frankly adding a lot of weight to the structures. Here I'm showing you, we had erected these 4 derricks in that space there. You can see the derricks. And what you see at the center here is the compression ring. See, this is the compression ring. Our erection procedure was, we put up these 4 derricks right now. We lifted the compression ring from this base up to 20 meters high. You can see it here. We 20 meters from the base and 11 meters from the springing level. So you can see we are holding it here in position. And then we start with erecting the petals. The petals would move from here to here. You can see in this photograph some bases that we have generated for the petals. This, picking up all this and taking it up was a really tedious process, because this compression ring itself was weighing around 2.5 tons. So we could have done it maybe in 4 derricks, but we preferred it doing, and lifting it again is a, by manual means, is a very tedious process, because every you can say the speed of lifting was around 2 mm per half minute or so, or you can say 5 mm per minute. We had to take it there. We had to ensure that it was correct. Again, the biggest problem was ensuring the levels. Our lasers, etc., whatever machines we have, those say, they say the accuracy is 50 meters. We could not rely on them. So we had to use some virtual, total stations, cross-checking. We went to the adjacent buildings, checked the levels, etc. So this was the biggest step in our first. Then you can see this is one petal. I'm showing this photograph for you to get an idea of the scale of that petal and how that petal was, you can say, only in 2 different angles it would fit into the space that was available there. Otherwise, it was very difficult to maneuver there. And then these 4 derricks are in place. To lift up the petal, we had to have this, what we call as a gadam in local terms. And this was used, and we started using this. We thought, our first impression was, since my petal is hardly 11.5 meters, our gadam, which would go 8 meters plus 11.5 meters, would be enough for us to pick up the petal and place it here and then place it here. But then as we picked up the petal, we found that because of the shape, it would tend to fall in front or behind. And then whatever height, our first gadam was only up to here. We thought it would be very easy to pick it up here and then, pull it and, anchor it here. But then we realized that was not possible, and it was taking a lot of effort. And we were worried that nothing should, fall down there, because our whole building was below it. So we increased the height of this gadam to nearly 20 meters. And from here, we were able to lift this petal and place it here. And then people would go onto this derrick and ensure that it is held in the air. All these positions we see are the seats for the petals. We have marked them and, welded a sort of a seat cleat there to ensure that the petals would be properly in place. And then the whole welding and the bolting happened on inside there. This is when all the petals were erected. Now the biggest difficulty in this was, among all the other difficulties, was to ensure that, I'll just go back 1 or 2, here you can see, the derrick had to be erected, and also the derrick would have to be dismantled at some time for us to accommodate some of the petals, because you can see here that they would interfere with the petals. So during our analysis, we had to ensure that the whole dome would be stable for self-weight only when 12 petals were erected, and the 4 locations of the derricks were selected in such a way that they would take, diametrically opposite diagonal places, where when the derrick was removed, then those petals could be erected and the whole dome could be formed. So The whole analysis had to go in so many stages: completed stage, then the incremental analysis, loading stage. Then we also had to find out how to load the whole, whether we load it from below or we load it from above. Loading it from above would have been difficult, but loading from below also was, I mean, the getting the shape right was very critical. This is, you can say, the completed form of what we managed to do. The derricks were cut, two derricks were cut, and two were held in place till the next was placed, and then later on the whole thing was installed. These are just some design parameters. We normally go as per the IS code, all the loadings, the dead loads. In this case, it was very critical. The dead loads were very critical because the GRC, we again had to check the size of the panels, and the GRC thickness we computed both again for durability and for the size of the panels. It was around 50 mm. So generally you will find that the loading compared to other such domes, here the loading was quite excessive. The weight of the GRC itself was around 150 tons on this. Then the wind loads as per the code from one side, the other side also. Actually, we could have easily done it from one side only because it's a, as far as the dome is concerned, it's a perfectly symmetrical structure. But we preferred to check all the members from all sides. The wind loads were applied as required. And then we go on to the connections. Here you can see some diagonal bracings, the connections, and the petals were basically connected, plated, a three-plated system where we could have the flanges, the ribs, and slowly diminishing towards the top. Main issue was, again, I said, we had to look at the design and we had to ensure that the whole thing would remain stable. The most important thing that we did in this was, as we were erecting, once we had to, first we erected the trusses, and then we were monitoring the deflections of the trusses very minutely. We had put dial gauges on all the trusses, and then we would monitor them and ensure and try, correlate with our design analysis. Our analysis was first just the sulfate of the structure completed, then the purlins added, GRP panels added on the first row, then the glass reinforced panels added on the second row, the third row. All this we did to, just estimate what would be the tentative deflection that would happen in the trusses. See, a 22-meter truss is quite a long structure, and because of its deflections also, there could be some secondary stresses in the dome, which we wanted to eliminate. So we had to monitor that, and you can see here just a cross section of the structure. This is the base where the petals would arise on the truss, the stiffeners for the truss. Again, this is a plan view of how we reinforce the RCC columns also with plates from all four sides, so that we could weld some elements to the RCC column also, and also our base plates and things were placed on top. I'll just take you through some deflection calculations also, just for your information. You can see we can analyze it in STAD and check the deflections, but as a second check, we tried doing this in by virtual work method, by adding a unit load and then checking. So we could just add the loads and check what would be the deflection. This was, you can say, the calculated deflection, 25.09 mm at the maximum loaded stage. And we also had to check the whole thing for thermal expansions. We found that the thermal expansions in Pune, it's a 20-degree difference between the day and the night temperatures, but the effect was not so huge. Maybe we could say because of the GRC, which is quite, this is, you can say, I would like to tell you that actually the measured deflection was around 20 mm. The calculated deflection though was 25 mm, but the measured deflection was 20. Here is just a view when all the petals and the insulation panels were erected. You can see the trusses below the panels, and the architect was also happy with showing the skeleton here. because that would add to the design. These are when most of the GRC, this stage is when most of the last reinforced panels were done, or they are nearly being completed. And this is a photograph of the completed structure. This photograph was taken, I think, on the Independence Day celebrations, where the whole building was suitably lighted, and we are very happy with the results. In fact, the corporation people were also quite happy, and there is a local, you can say, Architect and Engineers Association in Pune, which took cognizance of our efforts and gave us an award for for the efforts that we took in design and erection of the structures. I think that is all. Over to you, Mr. Abhay.
Thank you.
Thank you.
Well presented, the team of Mr. Shirish and Mr. Bal Kulkarni.
Thank you, sir.
Thank you.
We'll discuss more on this once we reach to the end. Maybe we can switch over to the second presentation as of now. Domes in Indian history, in international heritage, have a very important role. And one of the very style thing about the dome is that they can be constructed, they have been constructed with several materials, not restricted to steel or concrete, but many different materials have been there. So when we reach to the question answer discussions, we'll discuss more on that. Let's be ready for the second presentation, second project. So maybe I can ask Manisha to invite our next project speaker for this.
Yes, over to you, Mr. Basu. You can start the screen sharing.
Good evening, everyone. I'm having a little trouble with the video, of course, but there's no trouble with the screen sharing. Thank you, Manisha, for the kind words. And thank you, Dr. Gupta, for introducing. It is a wonderful seminar, and I really thank MX Media for bringing all the panelists and the speakers together for this wonderful session on dome. Dome, of course, as Dr. Gupta has mentioned, is one of the most challenging structures which ever has faced in the history of all structural engineering. Now, of course, we have seen different types of domes being either concrete or steel. Here, there's a coverage on the steel dome. And so I'd like to present, are you being able to see my screen?
No, sir, we cannot see your screen.
You can screen it. Okay, thank you. So this is a solar dome. Why we call it?
1 minute. Your screen sharing is not on, sir. We cannot see your screen.
Okay.
We can now see it.
You can see it. Okay. Yeah. So we call it the solar dome, and this was conceptualized with the idea of spreading awareness on the solar panels or the solar usage of the renewable solar energy, which is probably one of the most sustainable form of energy in the future. So this dome was conceived by the West Bengal State Electricity Board, where it actually houses an amusement park inside, and the entire power system of the amusement park would be powered by the energy stored or received from the solar power, and the excess amount of power would be supplied back to the grid. So as you can see, this is a very virtual image of how the dome would actually look like. You can just see the solar panels being installed on that. Then this is exactly the way a solar panels would actually be installed on the dome. So as I mentioned, the client is West Bengal State Electricity Board, the project consultant being the Development Consultants Private Limited, and we being the structural consultant, that is BCE Design Services. And the project contractor was Bridge and Roof, who was took up the challenge of erecting this magnanimous. Basically, just to go by the little bit of background to this, this was actually the state's first complete renewable energy structure, and the entire park and the amusement, all the aquariums and the laser show areas and all the buildings inside this dome would be powered by the energy received from the solar power. The structural features of the dome. So basically the dome is around 45 meters diameter. It is not exactly an hemisphere, but it extends a little beyond the center. So as I mentioned, it's 12 degree beyond the semisphere of the dome. There is a viewing gallery in the middle, which I'll give you a big brief idea of where the viewing gallery is and what is the purpose of that once we proceed with the presentation. There are basically, this dome consists of double framing. The inner frame is the main core frame, which takes in all the structural loads. And then there's an outer frame, which houses the glass panels, and again, which also houses the solar panels. The inner frame is made up of a combination of the hollow sections and the built-up members, because of course the column sizes extended from a box section of 900 by 400 to 500 by 400. We have varied the column sections in order to save steel. So the inner core weighs around 350 tons. And then there's an outer frame which actually houses the glass panels and the solar panels. So that is again made up of hollow sections, again, which is approximately a tonnage of 100 tons. Now, one thing on the usage of hollow sections, you see hollow sections are very strong biaxially. And when any sort of circular or annular ring structures are made, be it water tank or be it domes, there's a huge amount of hoop stress which has to be catered to and taken care of. And this hoop stress is, though it's an axial force along the member, there are various other forces which are biaxial in nature. And hollow section is a very strong element in taking biaxial loading. So this is actually a 3D image of which is created from one of our 3D detailing softwares. And this image is actually has been actually replicated into detailed drawings, which I'll give you a brief idea in later stage. So if you can see, there are actually two core rings, and there's one single annular ring on the top, and then the second layer of annular rings. You see, as Mr. Kulkarni mentioned in his presentation, that yes, these are compression members, but these members are sustained to take in the hoop stress along with all the lateral members which are connecting to columns. So why the two annular rings? Because what happens is we have given columns at an angle of 15 degrees. So we have 24 sets of curved columns. Now, if we were to actually sustain this curved column into single annular ring, there would be a junction where we have a huge number of columns coming in, and the joints would actually be a little bit tough to weld and it would merge. So we kept the second level of annular ring in order to give the second level of column an ease to join. So, okay, so this is basically how a column section looks like. I'm not sure if you are able to see this. So this is the entire curvature of the column, and which starts with the box section of 900 by 400 at the base, and then it joins down to 750 by 400 and coming to 650 by 400, and then last segment being 500 into 400. These are all the box sections. Now, if you see, I've shown you a box section which is laid on the ground. Why I have shown you this picture is that to show you actually where we have put the butt weld. The reason is that I could have elongated the shorter direction plate and then had a butt weld on top, but you see that would have been given a problem while butt welding on the lower side. So the side butt welding, in order to give it a because this columns have to be fabricated and welded at site on the ground. So while being on the ground, the easiness of welding has been taken care of by welding it on the side. Now this project has a little bit of you see the detailing part of this project more than the analysis and the design part what was complicated and challenging was the detailing and the erection part. In the entire detailing was done in collaboration with Bridge and Roof, the engineers at site in Bridge and Roof. Their ease of erection, the logistics, all their instruments which are available, and the number of labors available. The reason is that accessibility to the site actually decided the length of the members and the splices locations. The box sections and the weld was bare, and the curvature of the column and the splices also decided whatever space, welding fabrication space was available at site, because this was not done in a very greenfield project site. They had building structures surrounding it. So all these details were taken care of. All the angles of all the hollow sections were jotted down. At each level and each angle, we were at the circular, annular ring members, the lateral members drafted out. If you can see this is how actually the fabrication at site would look like. This on the two sides, you see the shorter side of the box section, and in the longer side of the box section resting. Now, before we put the top section, we put the half-cut steel ribs, which are welded on both the longer side and the longer section. That is the higher sided of the columns. So once this is done, this is plate and fabricated at site, and then the top cover, which is the other longer side of the box section, are placed on top. So this is how a thing would look like once the box section is complete. Now, how the erection scheme of all the entire structure goes, which is the most critical. I think Mr. Kulkarni has also given a good presentation on the erection scheme as well. So over here, if you can see, there is this main core column line, which is called the main straight column line. This is the first set of curved column line which is to be erected at site. Now we have a center pylon, which again caters to the erection scheme. You'll see that in the next of the images, the site images we have with us. So this first frame is installed with the cranes and guy ropes to hold it in place, because it doesn't have any other frame on the perpendicular direction to hold it in place. So this, on the left hand side, you'll see that inside the dome, there are actually ramps going up, which are spiral in nature, but which is going up with the periphery. The ramp is to give access to the viewing galleries on the dome. And those ramps, you can see, they have the flat slab and the castellated beam concept have been envisaged for this, along with cantilever portal with a prop cantilever with a hanger coming from the main column holding the main platform curved platform beams. So this is while the installation of the first set of columns. You see the central pylon was designed such a way, and it has the guy ropes tied onto that. You can see that. And then you have the central box section being, once it's fabricated on the ground, it is being erected with the crane and resting on the pylon. Of course, the bolts and the anchor bolts and everything were cast in situ. So once we place the column, we go on for the second leg. So this is going for the second stage of installation. In the second stage of installation, the next perpendicular frame was installed. The second phase is basically, once you do this, you have a basic level of stable structure. That is column on all four sides. But yet, at this point of time, it is still not structurally stable if there are sudden cyclones or wind pressures. Now the second frame frames on or welds on to the first single frame, because the first single frame is a continuous frame and the second frame welds onto the first single frame. So that's how a second frame, once it was done, and how it looked like inside. So now we come to the concept of how we actually place the annular ring. Once these four column or this main two frames were erected, then we fabricated the first level of annular ring. You can see the central annular ring over there. That annular ring is actually hosting 8 numbers of further columns, which are originating exactly from the annular rings. Now, this annular ring was to transfer the forces to the main columns And then actually once entire thing was welded, it would act in a, again, at the similar way as that of a hoop stress. Once this annular ring was erected, the next set of all the 8 columns were erected after placement of the annular rings. You can see once the 8 columns again are erected. So now we come to the second level of annular ring. This second level of annular ring is also hosting single columns framing into that. So there are 10, if you can see that. So there are 6 on each side. There are 12 columns going into framing into the second level of annular ring. Now what this actually did was, if I didn't have the second level of annular ring, and if you projected those columns into the first annular ring, you will see all these columns merging into a single point, and their joints would actually merge in. So just to prevent this and make erection easier, so we had the second level, and that's how it actually is supposed to look once the second level of annular ring are placed. You have 24 sets of columns now ready and in frame in action for the dome. Now, once this was done, we had obviously, while doing the design stage, we had to decide on the splice pattern. Now, if you see the splice pattern, so there are, in a box section, there are the 2 longer sides and there are 2 shorter sides. The splice was entirely decided to be staggered form, so that the shear forces don't transfer, or the shear plane does not lie in the same location. Now this splice of the shorter leg was retreated behind on the top, and it extended in the bottom shorter leg. But for the sides, it was in an angular form and not in a straight perpendicular form to the member. Once the splice was erected, once the splice was done, the second set of the box section would come and frame onto that. If you can see this, so this is how exactly a splice would look like. And this is the angle form of the side longer sections. You may notice that the tack welding is initially done because these are curved members. You can't do a run through first straight weld while doing a curved member. So you initially need to tack weld it. Once the tack welding is done and the member curvature has been reached, which was not going to curve further, then the running weld throughout the joint was done. Now, these splices were kept at a location of 1000 millimeters from the change of sections. If you notice over here, as I mentioned earlier, we have 4 sections of box sections patterns which we have used. That's 400 by 900, 400 by 750, 400 by 650, and 400 by 500. So wherever there is a transition of section size, we have kept the splice section 1000 millimeter below that, so that the splice bending and the splice forces are not part of the transition forces between the 2 box sections. The next part was the installation of bracing. Now, if you can see, there is a single main core level of bracing at one layer. This layer is, we have given X, we call it the X, or the tension bracing. And these bracing detailings were done based on the erection scheme. How? So what we were doing was, once the columns were erected, the first framing would be done for the bracings is that you had the gussets connected to the column, and then these hollow section members which were used as the bracing had slits in the middle. These members were slid inside the gussets and then placed in position. Once it's in position, it was welded to the gusset. The slots were welded to the gusset. Once the first stage of erection was done, in the second stage, the cut piece member, the cut piece bracing was first slit into the gusset, which is on the left hand side, left and bottom corner. Then the member was rotated to fit in to the main continuous bracing level. Once it fit in, then it was welded to the main bracing, that's a continuous bracing member, as a continuous butt weld. Once these two were erected, second came the second bracing from top. It was slid inside from the top, and once it was slid inside, it would be rotated and then into meet the other continuous bracing member. And then again, just like the lower bottom left hand corner bracing, we weld this to the main continuous bracing member. So that's actually how it would look like. Now we have the bracing member now. Now then comes the lateral member, which would be slid inside again to those gussets and then welded. Now, one thing I must tell you over here, these lateral members, whatever you see, are actually perpendicular to the curvature of column. All these lateral hollow sections were bent. Not only they were horizontally bent, and after horizontal bending, they were actually split. They were actually rotated at a degree, and the gussets were also placed at such a degree that it would be the lateral major axis of the column for the lateral member would be in the perpendicular to the curvature of the column. So this is actually how the side pictures were looking like. There are two images. One on the right hand side showing how the bracings were slit inside the gusset and the central part being welded. And on the side, left hand side, you can see an image of the gusset and the hollow sections. Once they were slit inside, they were welded directly on site. That's at the erection level. Now the third part, the fifth stage was to erect the top horizontal member, because once the cross bracings were done, the bottom horizontal and then followed by the top horizontal would be placed in position and then again welded with the gusset. You can see that these horizontal members have attained a curvature. They are not straight members. All of these horizontal laterals were all in the same curvature as that of the dome. This is a typical picture of some of the joints we had used. If you can see that, so there's a central column and then you have the hollow sections framing onto it from the side. What you can't see is that the hollow sections are actually perpendicular to the curvature of the column. This is because this is in section. We are unable to show you the curvature. But however, if you look at the right hand bottom corner of the image, you can see the curvature, the hollow section. This is the second framing of the hollow section, mind you. This is the outer frame, the second bar, the lower bottom right hand corner image. This outer frame is again made of hollow section, as I mentioned. This is actually holding the glass panel and the solar panels. Now, Calcutta again has a temperature variation of 23 degree to 27 degrees centigrade. So these glass panels, which were within the solar panels, were exposed to expansion. So we developed a joint, or if you can see on the left hand bottom corner, it's called the expandable glass panel joint. These joints would expand during any thermal expansion, and yet because of its locking nature, it does not allow any sort of air passing through the glasses. And these were screwed onto the hollow section framing members. And this again, this joint was designed and developed only to host the glass panels, so that the expansion could be taken care of. Now, this is basically what the dome had. There's a viewing gallery in the middle. There's an entrance at the base, and there are 4 entrances to this hollow section, to this dome. There are the glass panels in the inner frame, and then there are the solar panels outside the glass panels. Basically, the solar panels cover the dome in such a manner that you can't see the glass panels, but the glass panel intention is to prevent any air or it acts as a facading member. The glass panels actually had to be designed and cut based on the the curvature of that particular slot, which is approximately a curvature trapezoidal. If you can see over here, you will have a fair enough idea of the size of the glass panels which were being used. And each of these glass panels, they were not rectangle actually they were a little bit of trapezoidal with the curved trapezoidal. And these were framed onto these hollow sections in a curvature which was to be manufactured by the glass manufacturer, which was who were part of this project. Now, just as some of the pictures of the site where the construction of the dome was included. So this is while welding and then smoothing out the welding joints, because after you weld it, you need to graze the weld in order to attain a smooth weld. And you can see that everything was done on site. And on the left hand side, you can see an image of the curve we had attained via the plate. Because of the hollow section, plates are easy to curve in and then form for the column curvature. So over here again, you can see these are the splice joints, and the bottom ribs, that's the bottom short member coming out and the top member receding in, and then you have the slope of the sides. So these were same pattern followed for all columns. We did conduct some of the ultrasonic testing and the dye penetration test for all the welds. And because we needed to check all the welds, because once it was erected, it wouldn't be easy to check any sort of welding joints. All the column welded joints were checked at site on the ground. But yes, even after erection, there were weld tests conducted at various random levels to understand the weld being, that is the lateral members, when they were welded at the columns, they did not have any bubbles or any sort of openings. Again, as I told you, the third leg being erected. Now, these erections, once this erection process was done of the 4 members, after the first annular ring, the 5th leg was being erected. Now, the entire thing, if you can see, was actually resting on a single pylon design, which had guy ropes to the ground. And this pylon was actually designed to sustain any sort of lateral frame pressure which would arise from any sort of wind load coming onto the fabricated or erected columns. This was a stage-by-stage progress of the entire dome being built. Once the first level of annular ring was done, all the 8 set of columns which were to be connecting to the annular rings were erected. And then again, the second level of annular rings made sure of the remaining set. Now, while the columns were being erected, there was a request from the client to have a mock-up session of the solar panels and its connection to the main column and how it would look, and the mock-up session of the glass panels inside, whether it would actually be wind resistant or not. So they erected some of the lateral members. You can see, you may be able to understand that there is a curvature to these lateral frames. Once the lateral frames for the mock-up sessions were done, this is just to have a simple idea of how the glass panels would look like. This is actually after the installation of the structural members, which would actually host the glass panels and also the solar panels. You can see the white, the semi-gray solar panel fixing frames. Once this was done, but these were done after the first annular ring, before the second annular ring was done, corrected. This is how the solar panel would actually look like. And if you see, there are glass panels behind that. So basically, there are gaps within the solar panel, but then those gaps were of just because of the solar panel dimensioning, and the entire dome would actually be covered with glass. So this is actually how the after the erection of all the columns and the bracing the dome and the second level of framing the dome were looking like. And today we have the dome. It's still in construction, and the dome actually has the solar panel and the glass fixing panels going on. You can see the panels fixing. Those semi-gray white members are the glass panel fixing thing. And this is basically the entrance, the first main entrance to the solar panel. And there are the internal building members, which is actually a concrete building, still being built inside. Basically, this is an amusement park. And of course, as I mentioned earlier, that once the dome is inaugurated and the dome is in use, the entire power of this entire amusement park will be supplied by the solar panels of the dome, and the excess power would be supplied to the grid. Thank you. That will be all.
Thank you so much, Mr. Basu. It's really a very interesting project that you have presented. By itself, amusement park is something different, and the visitors would expect many good things, and in that a solar powered dome is an added feature.
Yes.
It was well made with all the aspects of design, construction, and everything. We are now on the question answer, and there are some very interesting
So I'll
points.
just make a quick announcement before the Q&A.
Okay, please.
So request all the participants to please participate in the poll, and also do write your feedback to edit@mxbm.in, and glance through our latest interactive issue of SSMB magazine. Before we start the Q&A session, I request Carol to make the announcement.
Before we move on to the Q&A session, I would like to announce for the next webinar, which is a continuation of the tech village that we had earlier, which would be on construction challenges of the same, the episode 2, with the contractor and the steel supplier on board. The speakers for the next session would be Mr. Hariom Gera, Mr. Tapas Mathur, Mr. Ajay Agarwal, and Ms. Himani Joshi. So the registration link for the same is in your chat box. Do join us next week at the same time at 5 p.m. for our webinar. Thank you so much. Over to you, sir.
We now move on to the question answer.
Yes, sir.
Great. We have good number of people who have listened to both the presentation and have some very interesting things they have asked both the presenters. So I'll take up first with the PMC dome with Mr. Shirish and Bal Kulkarni ji. There are some questions related to the design, construction, and other aspects. We'll take up them. One is to start with what is the maximum and minimum D by H ratio permitted. It's basically with the geometry of the dome. So people wants to know, is there any set rules for the diameter to height ratios for an optimized design in case of domes?
If I can answer that.
Yeah,
please.
Basu can take up that.
The feel is that the H by D ratio, that's the height to span ratio of the dome.
Can we see your face also?
I'm having trouble with the video. I'm not
Okay,
sure.
okay. That's good.
Great. So the H by D ratio generally, it would be good if you have a H by D between 0.25 to 0.3. It is seen that in this ratio, the maximum, the buckling and the moments and the deflection and the axial forces are all balanced out. Because once we have noticed beyond 0.4, the axial forces increases very rapidly. And up to 0.4, we have a gradual increase in the axial loads, axial forces. So I would recommend an H by D ratio of 0.3 to 0.25 to 0.3, which would be a really balanced H by D ratio for a dome structure.
Good. Any inputs from our other consultant, Bal Kulkarni ji?
Yeah, I would agree with Mr. Basu, but as he says, it would also depend upon the type of structure. If it's a concrete structure then maybe the H by D you would choose would be different, because again you have a monolithic structure, and all your stresses are going below. As he says, the shallower the dome, the lesser the forces. So you can decide your
I hope
geometry.
that satisfies. Is there any literature, any reference you would like to recommend for our audience, on the, in general, those who are interested in reading more about the domes?
There are some papers, technical papers published in Structural Research Journal. I'm not sure. I don't remember exactly where.
Okay. So those who are interested may send a mail to SSMB, and then probably we will be able to
Yes.
do them with the literature. There is a very interesting question about the material of the dome. We have seen both the steel domes, but certainly in the world we have seen many types of domes. I personally have worked on one of the largest bamboo dome. That was India Pavilion at Shanghai. That was a huge dome of 200-meter diameter, and it was India Pavilion. It was done by a Delhi-based architect only. We have seen ferro cement domes also, brickwork domes also. So somebody has asked, what are the challenges with concrete dome structures and steel dome structures? So if you would like to say something on that.
See, as far as design is concerned, I would say concrete are easier to design, easier to model. But the biggest problem is the weight. The weight is huge, and then you have to take care of lots of things. And also, when we have such odd spaces where you really have to fit it, again, you would have to have lots of formwork there, and so many things where you should be able to cast the concrete appropriately. So, I mean, domes in concrete, I would prefer, but then the situation should be that when I am allowed so much load, and when I'm able to cast the dome properly, and
So what parameters would be the decisive parameters, whether to go for a steel dome or a concrete dome?
I think one of the important thing is the location of the dome itself,
Very correct.
because that will determine how the whole thing can be erected. So based on that, one would have to kind of model the dome in the manner where it is going to be erected. I mean, constructing a dome where it is resting on a ground, then that the parameters would be different than where you are doing it on top of a multi-storied building.
also, I would say the sheer size of the dome. If I'm doing it maybe as we did on the 7th or 8th floor, and if we had done it in concrete, the weight of the whole structure would have been so much. And my columns which go down would, especially for the seismic effect, would be so thick, and the sizes would have been so much. Then it would have been not really feasible to accommodate so many spaces there. So I think that also would be another factor, where suppose it's a nuclear structure, yes, then I have I mean, my column sizes could be whatever I get for design. But when I'm looking at habitable structures or public figures, then I have to look at my overall, I mean, the total weight would determine the sizes. So I think the weight which are allowed would determine what sort of structure.
Efficiency of the spaces below should not get hampered because of the weight of the dome and the resulting structure below.
So function, then form follows the function that plays a role.
Yes.
How much was the weight of this PMC dome?
Total 350 tons, out of which the lower supporting structure was around 200 tons, and the upper structure was around 150 tons.
And I think the other one, Kolkata solar dome, was also almost in the same range.
Yeah, the inner frame was around 350, and the outer frame was around 100 tons. There are two framings. One is the main structural framing, and one is the main facade framing.
Mr. Vireshwara Rao Yelugari, why can't we use assembly of 4 ribs and compression ring, since the tonnage is less and those can be installed together? This is for the PMC dome Deva, but it is in general a question. Why can't we use assembly of 4 ribs and compression ring.
No, see, the geometry is based on a square base and becoming a hemisphere. So it has to be first converted into a polygon, a 16-sided polygon. That is the one part. And fewer number of ribs would mean that the covering panels would be of a larger size. With the 16-sided structure, we could have panels which were not wider than 4.5 meters by 1.2. So it was a challenge of hoisting those panels from the ground to the top as well. So if you have lesser number of ribs, that means the panel size would be larger, and then that would be a handicap, getting it on top of at 20 meters and then assembling it on the top.
Correct.
Once you have four, just to answer that, see, if you have 4 ribs, then your columns don't act as a dome column. It's your beam which are bended, because the beam curvature will be large. Just what Mr. mentioned, because of the panel size, the beams have to be curved at a much larger diameter. Yeah. And then the main load-bearing members become the beam and not the column. Over here, at this sort of beams, it's the beams for the actual members, and the main bending members are the columns. That's the whole. That's actually the concept of a dome. Once you have 4 ribs,
domical behavior, we need to have more ribs, basically.
Of course, otherwise the vertical member will act as a main bending member in dome.
And as you say, the sheer size of especially the Calcutta dome is so much that 4 ribs would just defeat the purpose there.
Not at all. Have a dome. It will not be a dome then.
I think that question would be maybe related to the erection stage. Why? I mean, if that is what they are trying to ask, is why 4 ribs and a compression ring was not prepared on the ground and then hauled up and put together. I think we have already answered the question in the sense it was just not possible to put a crane anywhere outside.
Space-wise.
People are interested to know about the softwares used. So for both of you, I would like to know which software has been used for analysis, design, and which for the detailing.
I just like Mr. Kulkarni has mentioned, he has already mentioned that he's used STAD. That's also widely accepted, and even we have used that definitely for, because these are basic steel structures, and you can actually model domes and in a curvature in STAD. That's definitely, it's absolutely good enough, and there's no software specific. And honestly speaking, in dome structures, more than the analysis part, it's the connections and the erection scheme and the fabrication drawing which dominate. The analysis and design part is quite a little bit. Yes, what we have to do is that what Mr. Kulkarni and I has very beautifully shown, and we also have the same thing, is the load combinations used. You see, what happens is while erecting the dome, we have to ensure that all the ribs are not erected at the same time. So all the analysis should take in for the 2 legs, and then the 4 legs, and then the 8 legs, and then the 16 legs. All these things, all the legs and the erection stage construction, all have to be analyzed. Otherwise, obviously the whole purpose of construction.
Yes, sometimes you'll see that when you're doing this dome, when it's you analyze the whole model, say 16 ribs, and then you model only 6 ribs, you will find that the rib required would be much higher. So you have to take care of all this. It's not just, one software, but yes, at the end of the day, you end up doing at least 10 to 12 different models for different load conditions and erection conditions also.
Yes.
So yes, we prefer STAD for steel structures.
You did the stage analysis. Basically, the stage analysis has been done.
Yeah.
And for detailing, you must have used Tekla.
Yes, we used Tekla for detailing purely.
Okay.
We have preferred to do most of our connections by first principles itself, because we had all the forces, and these connections were relatively, you can say, monotonous. So we could design one rib and carry it forward to everything else.
But fabrication detailing you did in Tekla?
No, we did it. We drafted it. We actually use a software called Multi-Suit Steel, which we use instead of Tekla, and we did all that in Multi-Suit.
Multi-tools.
Multi-Suit Steel. Yeah.
Okay. Excellent. Very good. There is a general question for both of you. What treatment was done on the steel? Because some corrosion is seen in some of the components. So finally, for a longer life, you must have done some.
What we did was we had a special chemical from a manufacturer here called Dimple Chemicals, who are
Okay.
experts in anti-corrosive treatments. So they had given us a spray which was an anti-corrosive, which we used as a base, as a primer, you can say. We had that, and they had assured us that only one coat of that would be sufficient instead of the usual 2 coats of zinc oxide primers we used. And then we had 2 coats of enamel paint on it.
Very good. And the Kolkata dome?
Yes, it's basically zinc oxide. There are 2 primer coats have been done. Of course, there are some questions that I noticed that they are, I mean, at the look of the picture, and it looks like that the application of paints were not done. No, the planes were very much upright. Yes, because of the time and because of exposure to the air. But yes, the second coat, first coat is always applicable before doing the box sections, which that is grazing with sandpaper, sandblasting, and then putting the coat. The next level of coat comes in after once the erection is done. Obviously, the second level of coating comes, and then comes the final painting. All of them are being taken care of. There are no loopholes regarding corrosion on the steel structures.
Dr. S.K. Sharma from Indore wants to know whether the dynamic analysis was performed in both the dome cases.
Firstly, being a steel structure, obviously, it is much more wind dominated than seismic dominated structure. That's generally a steel structure where wind generally governs. So dynamic analysis of wind, we have, I mean, the softwares are yet to do it nowadays. Bentley is yet to install dynamic analysis of wind, because it will be the first software to have a dynamic analysis of wind. That's number one. But yes, the wind pressures were calculated at different angles and the different the variations of all things using all the codal provisions for curved structures. But no dynamic analysis was done for the wind. Yes, but we did, which again was not the governing force for this.
In Pune dome, whether any seismic dynamic analysis was done?
We had experimented with that when we had checked whether it was the dominating load combination, but we realized it was not. The dead load, live loads, and the wind load conditions. In our case, the dead loads were much higher, so they were dominating most of the time. And yes, for the base, the dynamic effects were, I mean, after the dome structure was transferring the loads to a lower structure, yes, it was. But the dome was, I mean, the dynamic effects of the dome were not
But the dynamic effect from the lower structure must have been transferred to the dome which is installed above. So that combined model you must have studied.
Yeah. We had to do the combined model also, and then for design the individual models.
Correct. Good. Aditi, hota hai, in the solar dome, how does the panels facing north produce the power?
Yeah, actually, that's a very good pertinent question for solar panels. You see, what happens is not all the solar panels are active at the same time. The power of 180 kilowatt, which has been calculated for the supply of the dome, is based on one. It's not exactly a semisphere, a little more than the semisphere, but each and every panel, whatever power consumption starting from 100% to 10 to 15% has been taken care to, and their calculation done. Yeah, she's right that yes, not all the solar panels are exposed to sun, and that's exactly the way the dome has been designed. The panel electric supply has been designed.
Great. Correct. That's good. The second level of the hoop ring in the solar dome, whether it was welded at top or bolted?
Absolutely welded at top.
Welded at top, on site itself.
Yes.
Then only it will give a proper rigidity. Somebody has also suggested that the cross bracings which you have shown, rather than welding them, could it not have been bolted for faster working?
See, this question I understand, and I keep on facing. You have to understand something. When I'm using a hollow section, and if I have to bolt it, and it has to be outside the surface of it.
At the same line.
It has to be more than the hollow section cross section, which looks very ugly, and I would definitely not want to follow that. If you study structures abroad, where direct welding is prominently and quite dominantly used for composite buildings. It's not that they have to use those plated, and they avoid excess plate size and bolting. So direct welding is a very, very good, very structures.
All those details you must have worked out from Tekla, and then the specific length of the members prepared.
Also, I would like to what Mr. Basu is saying. In this case, as we say here, the rigidity of the whole covering is also very important. It is not that we are allowing like a beam column structure, the beams can deflect a bit here because of the GRP panels. If there are, I mean, if we just provide minimum, say 2 bolts there tends to be a little bit of play in the members because of the gap that we, in such cases, and especially in both the domes, that is not preferred actually. So welding gives me appropriate stiffness and also the necessary, you can say, the dimensional stability also. So we prefer welding most of the time.
Absolutely, I agree with him. I agree with this.
There is a general question again. What is the ratio of the weight of the dome to the volume covered in the dome? Just general weight of the dome. Some efficiency kind of things.
I don't know. We have not worked it out, but generally I would say it would depend upon the diameter and the type of loading on the dome. It would vary, so it would be very difficult to generalize.
You know, I will actually answer. You know, steel structures, there's a predominantly people's question in the mind that consumption of steel is based on square feet. Well, the dome doesn't follow the conventional
Exactly.
tonnage area, square kg per square feet. No, it doesn't. Neither does it have any particular volume to follow.
What the geometry and the type of dome that we prefer is going to make a big difference.
Agreed. Sanjay Chaudhary asks from Mr. Nilanjan Basu, from the erection process, it is obvious that it took enough time, which would have resulted in corrosion in the inside surfaces of the built-up hollow member. There is painting inside. How corrosion is prevented inside the hollow box section?
See, as I told you, all the plates are first coated, and then the welding is done. And no sections are generally kept outside on into exposed water or rain. What you see, the pictures are all on-site pictures, but no structures, plates are exposed, and that's number one. What is important, what he has pointed out pretty rightly, is that the inside corrosion. Yes, the plates are first coat of painting is and the primer has already been applied before going on for the fabrication of hollow section. Second coat, of course, applies after the fabrication is done.
Have you used the high strength friction grip kind of connections anywhere in the base or somewhere?
No, the bolts are high strength bolts, definitely ACS 8070 bolts, but no other high strength connections have been used inside the structure.
Inside this.
Only at the base.
Srinivastav is asking, central rings supporting the petals may be subjected to torsion. So then how to tackle such torsion? Whether any torsion was observed in the analysis?
No, absolutely not.
There was any torsion.
Totally symmetrical structure and equally loaded from all sides. So there was no torsion.
And it was erected quite symmetrically.
So actually, central rings don't have in a dome structure will not be undergoing torsion, because those rings, the laterals are subject to only axial. The torsions can only come in if there are members framing in on a unsymmetrical member framing in, which is carrying axial load to give it onto that. This torsion over here is very negligible. Whatever if at all these forces at all it can generate, it is very negligible, because these are all restrained axial force carrying member laterally, working only on hoop stress.
Yeah, very true.
There's a very interesting question by Mr. Ajay Jadhav. Whether any wind tunnel testing was performed or straight away the wind forces taken from the code?
No, there was no wind tunnel testing performed, because relatively, if you look at the height, it's not much. I mean, the total height was around 40 meters. So, I mean, we didn't feel there was any need for wind tunnel testing here. It's not what I would call a slender structure. In fact, it's
and you were able to get the wind pressure coefficient from the code adequately.
Exactly, exactly. And it's a base heavy structure. So,
somewhere someone has noticed that
Sir, I
slender
can
structure. So
add to Mr. Kulkarni's word. The wind tunnel actually would have been performed analyzing that I am actually erecting my facade, be it the fiberglass frame or be it concrete glass frame or the glass frames, have it been on one side and the second side has been remaining empty so that to create a suction wind tunnel force. This is not actually the case. This is not so critical as that of what we are thinking, and because those forces get dissipated very easily. The wind tunnel action is not so much predominant over here in dome structures over here.
He wants to know, since the dome was placed at the top, being a heavy lumped mass, have the frequencies of the individual modes have been checked for resonance in case of PMC dome?
sorry, sir, I didn't understand the question. It is one structure. I mean,
Yeah, as the dome was placed at the top of the building,
yeah.
so the mode of oscillation, the frequencies of the individual models means
The
that,
lower structure they're saying,
yeah, lower and the dome.
it was positively checked because, as we say, the lower structure had to be designed for everything that we normally, the code specifies, the 1893 code, and again the lower structure was seismic dominant, so all the individual modes and everything were checked.
Correct. Somewhere somebody noticed that IS 800 1984 you have
Yes.
mentioned.
Yeah, we started the design as per the old code, but then we also had the whole thing vetted from engineering institute, and then we again tested it and tried it with the latest 2007 code LSD methods also.
Okay, that's very good. Very. When you are for the PMC dome, when you have made the fabricated box sections, so there were long stretches of welding which must have been done. Such may cause torsion of the box section. So whether any preventive measures or precautions were taken?
Yeah, I think I mentioned in one of the slides that you see all these box sections, curve sections are first tack welded. No long running welds are done in the beginning. Once the tack welding is done, the plate reaches its maximum level of curvature. Once that happens, go further, and after tack welding, if you ever run a full long stretch of weld, it will not curve again. So there's no question of any more further torsion. And there are ribs to half-cut ribs to resist that bit of lateral bending of the plate, in-plane bending of the main long side members. We have already placed that.
Okay, very good. The type of support conditions which were defined in the analysis, you made them simple support spin base or?
See, for box section, we have to have fixed because box section means having the bolts outside the section area. So once that the bolts are outside, it's a fixed connection. You cannot have a pin connection unless you face the bolts inside and then the box goes over the bolts. No, it's not that.
Correct.
Fixed connection.
Because of the end configuration itself, it becomes a rigid connection.
Yes, it has to.
Very good. Unless and until I convert that to a single point.
Yes, I convert that and place the bolts inside the box, and I have a belt. But that's very difficult situation.
Very difficult.
Very difficult to take.
And as we see, if you look at the sheer size of the dome, the number of bolts that are required are quite large.
Oh yes.
To fit in, then we unnecessarily have to increase the size of the member. So we preferred fixed spaces.
Oh yes, definitely. Fixed is
True. Very good. I saw in Kolkata dome that there were some platforms suspended. There was a spiral staircase, I think, going up.
It's a ramp actually. It's a spiral.
It's a ramp.
And it's a composite structure where you actually have metal decks with shear studs and actually a ramp going out. And it's at the end of the ramp, though it has been designed as a cantilever, pure cantilever, but it behaves like a prop cantilever because we have hangers from the top holding up the beam. Now that ramp is basically for the people to just walk up and then come to the viewing gallery. It's on the periphery itself. That's it.
So this dome is finished, completed? It is ready?
No. It's still in the construction stage. And the last image which I gave in the presentation is the final, what is the present status of the dome.
Very good. With this, we come to the end of the question answers. But if the audience, if our listeners have more questions, they can certainly mail to the MX Business Media, and we would be happy to address them. On the dome side, it's really a fantastic, very encouraging structure per se. As a structural engineer, we do not very oftenly use a dome in the common practice.
Yes.
In the things in the industry, we don't use them, but certainly wheresoever used, they really form a very good form of the building structure. They are very architecturally soothing and very useful. The way the concept which you have shown going a ramp up, that gives a very good idea that you can have several such suspended platforms or spaces which can be used in the domes. And domes are very sturdy structure for that matter.
Absolutely.
We have worked with aluminum domes, bamboo domes, ferro cement domes, brick domes, steel domes, concrete domes, stone domes. I have read on the literature that best dome in the world are the Sanchi stupas near Bhopal. They are stone domes. So Sanchi stupas, we should be proud of that they are still existing. Somewhere 100 BC they are like that. So very, very old domes and heritage. Otherwise, worldwide our audience can check. There are some very good domes which have been made in various things. So with this, we come to the end of the question answer, and maybe I hand over to Avneet for further proceedings.
Thank you, Mr. Gupta. Thank you so much. Thank you, Nilanjan. Thank you, Kulkarni ji, Shishir ji. This was a very fantastic and very engaging discussion. And I am glad that we went so much in detail along with the design, along with the architecture, the entire erection sequence we have discussed. I think that's amazing, the effort that each speaker has put. And special thanks to Dr. Gupta, who have kind of bedded the entire discussion into a very interesting story. Thank you all for joining us today. And we certainly look forward to have more engaging discussion with the speakers and obviously with the audience next Friday at the same time. Please register. The link is there in your chat box. And we look forward to see you